Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into Fortune's algorithm for generating Voronoi diagrams. It's a fascinating, albeit challenging, algorithm. Let's get started.
I'm eager to hear about this. I've heard it's computationally intensive, but the results are visually stunning. What's the core idea behind Fortune's algorithm?
Exactly. The visual appeal is undeniable. The algorithm uses a sweep line that moves across the plane from left to right. As it sweeps, it creates parabolic arcs around each site, or seed point. These arcs form the beach line, which represents the frontier of the Voronoi cells under construction.
So, the beach line is dynamically updated as the sweep line progresses? That sounds computationally expensive. How does it manage the complexity?
You're right, it's not trivial. The key is that we don't process every pixel. Instead, we focus on events, site events, when the sweep line encounters a new site, and circle events, when three arcs on the beach line intersect, forming a Voronoi vertex.
Ah, I see. So, the algorithm efficiently handles these events, rather than brute forcing every point. But what about the parabolic arcs themselves? How are they represented and manipulated?
That's where the cleverness really shines. Instead of using the standard parabolic equation, the algorithm uses a locus definition. Each parabola is defined by a focus point, the site, and a directrix, the sweep line. This makes calculating intersections much easier.
That's elegant. Using the locus definition simplifies intersection calculations. But how does the algorithm determine when and where to create Voronoi vertices and edges?
Precisely. Voronoi vertices are created during circle events. When three arcs intersect, their circumcenter becomes a Voronoi vertex. Edges are formed by connecting these vertices. The algorithm cleverly tracks incomplete edges, which are extended as the sweep line moves, eventually forming complete edges.
So the algorithm maintains a data structure to track these incomplete edges? What kind of data structure is used?
Yes, it uses a doubly connected edge list, DCEL, a common data structure for representing planar graphs. It's quite intricate, but it allows for efficient manipulation of the Voronoi diagram as it's being constructed. It's a bit complex, but it's what makes the algorithm so powerful.
I can imagine. The article mentions that even with this optimized approach, for most practical applications, a simpler O(n)² algorithm or a library might be preferable. Why is that?
Yeah, that's a good point. While Fortune's algorithm boasts O(n) log n time complexity, the constant factors involved can make it less efficient than simpler O(n)² methods for smaller datasets. The implementation complexity also adds overhead. For many use cases, the performance gain isn't worth the added complexity.
That makes sense. It's a trade-off between theoretical efficiency and practical implementation. So, in summary, Fortune's algorithm is a powerful but complex algorithm that uses a sweep line and parabolic arcs to efficiently generate Voronoi diagrams. It's a beautiful example of algorithmic elegance, but perhaps not always the most practical choice.
Exactly. It's a testament to the ingenuity of computational geometry. But as the author wisely notes, unless you're dealing with a very high volume of large diagrams, simpler approaches might be more suitable. Thanks for joining us on Tech Bytes and News. We hope you enjoyed this deep dive into Fortune's algorithm. Goodbye.
Bye-bye.